Good morning, good afternoon, wherever you may be in your day. Thank you as always for choosing the general chemistry part of that day. We're going to continue with the ideal gas law. We're going to do more of those PV equals nRT calculations. We're going to tie in the idea of if we have a mixture versus a pure gas. Okay, so basically Dalton's law is that each gas is going to exert its own pressure. So what's this mean from a practical standpoint is that the total pressure, and again, when we measure something, we put a barometer out, everything hits it, right? It's collisions of these gas particles, everything hits it. So we can't say, oh please, Mr. Nitrogen molecules, could you just not hit this surface and just let the other ones do it? So when you're measuring a pressure, you get a pressure in a word problem, just realize it's going to be the total pressure. And total pressure is the sum of the individual pressures. Generically 1, 2, 3, we call those partial pressures because they're a piece of the whole thing. And so for example, in this room, or the room you're sitting in right now, the pressure in the room is it's a sum of the pressure due to nitrogen, the partial pressure of oxygen, partial pressure of water, partial pressure of CO2, partial pressure of argon, hydrogen, etc., etc. Without getting into the math, if you start to extrapolate this out, what you realize is that total pressure that we measure, the volume doesn't matter because everything takes the shape of the container. So all these individual gases have the same volume, so we can just put V. And they're all in the same room, they're all touching, so they have the same temperature too, so we don't have to individualize that. And the kind of interesting thing about the ideal gas law is that every gas molecule behaves the same. So a teeny tiny hydrogen molecule with a mass of 2 hits with the same pressure, the same force as a radon molecule with a mass of 222. How is that possible? Well, if I wad up this piece of paper and I throw it like that, it's not really going to hurt the board. Or if I throw it like this, it's not going to really hurt me in the head. But if I were to take a bowling ball, which weighs a lot more, and do the same thing, it would probably hurt me in the head. That being said, if I were to slowly roll a bowling ball into my hand, it's not going to hurt. Whereas if I threw this with enough force, I could actually probably hurt myself and at least scratch my eye or something if I were to throw this hard enough. So there's two pieces to that, right? If you're talking about the force, it's the speed at which it hits and then also the mass that it has. So enough out of that. Let's go back to this idea. So what's interesting out of the ideal gas law is all of them hit with the same force. Lighter things move faster and makes up for it. So they're all having that same pressure, so we can basically treat all gas molecules generically the same. So the total number of moles of gas will give us the total pressure. And if we take this out another piece, what it's really saying is if 20% of the molecules in a room are nitrogen, 20% of the pressure is nitrogen. If 14% of the molecules are propane, 14% of the pressure is due to propane. So what is this percentage ratio type idea? It's called the mole fraction. So the mole fraction is the funny Greek X guy. So subscript A, so gas A, so this could be oxygen, nitrogen, methane, something like that, CO2. So the mole fraction of A is equal to the mole of A over the total moles in the whole thing. So like I said, if it was 10%, it would be 10 over 100, that kind of idea. That would be the ratio. So you take that ratio, multiply by the total pressure, and you get the individual pressures of the partial pressures. So the starred parts are what I expect you to know and be able to use mathematically. What's that look like in a problem? Excellent question. Okay, so a flask with so let's just do a concept check, going back to what I just talked about. A flask with 3 moles of hydrogen gas has 3 moles of argon gas added to it, sealed container. What happens to the pressure of hydrogen when that argon gas gets added in? And this is, I find if I ask this question on tests, a lot of people will get this wrong, and they'll get it wrong even when I warn them it's coming. This idea that we add argon gas, it's got to do something to the pressure. But if we're looking, it's asking the pressure of hydrogen. What's the partial pressure of hydrogen? Well, if we add argon, does that change the number of hydrogen molecules or how often those hydrogen molecules strike the outside of the container or the temperature of those hydrogen molecules? And the answer is no. So this really has no effect. So nothing is the answer. So if you add in another gas, it doesn't affect your calculations, it doesn't affect the pressure. It affects the total pressure. Obviously, the container has more things in it, but not of the hydrogen. So let's go back to this idea. How do the pressures compare? Argon weighs a lot more than hydrogen, so Doesn't matter. Ideal gas law, gas is a gas. So these are going to be the same. If you have equal moles, you have equal pressure. And then the total pressure, well, the total pressure is going to be the pressure of the hydrogen plus the pressure of the argon. And since they're equal, I mean, you could actually say the total pressure is going to be 2 times the partial pressure of hydrogen or 2 times the pressure of argon. If you knew one of them, you could just double them because they're both the same. So that general idea of how do you put this together. Another more sophisticated, complicated way of looking at this is let's take water. We apply energy to water, and we sorry, it's past my bedtime. It's a little late for me. We take the water, we split it with energy, and we'll get hydrogen gas and oxygen gas. And if we did this into an empty container and we collected the gas, and let's say we measured the pressure at 6 atmospheres, is this enough to tell me what the pressure of hydrogen and oxygen would be? In a way, it really is, because if we assume every gas molecule exerts the same amount of pressure, we know that the pressure of hydrogen is going to be twice as much as oxygen. Or if we look at this, if we were doing mole fraction, the mole fraction of hydrogen is going to be 2 over 3. 2 moles of hydrogen for every 3 moles total. Multiply that times our total pressure of 6 atmospheres, and all of a sudden we get 4 atmospheres for hydrogen. And we could subtract that 4 from the 6, and that would give me 2 atmospheres for the oxygen. Or we could do 1 over 3 with the mole fraction, so same idea. So again, you can kind of logic your way through some of these ideas. 2 more concepts before I'll stop this video, and then I'll break this into another one where we do the longer calculations. But just the short kind of concept-y calculations. The pressure in Radford is typically about 0.91 atmospheres. If the air is 78% nitrogen, what's the partial pressure of nitrogen? So again, this is as simple as pressure of nitrogen is the mole fraction of nitrogen times the total pressure. Or in this case, if it's 78%, that's 78 out of every 100 molecules times 0.91 atmospheres gives me my answer. I get 0.71 ATMs as the partial pressure of nitrogen. I like the pictures because this gets at the concept. So we got this little mixture down here. We can see 3 different molecules, 3 different gases. There's the diatomic blue, the monatomic orange, and the one that kind of looks like CO2 there with the pink and the green airs. If I put a barometer in there, some pressure measuring device, and it comes out with 700 torr as my pressure, what would be the pressure of orange? So again, this is that whole concept idea. So if we look at the orange, I count 1, 2, 3, 4. If I look at how many molecules there are, I count 1, 2, 3, 4, 5, 6, 7, 8, 9. And again, it doesn't matter how many atoms, we're looking at molecules. So 4/9 times 700 gives me an answer. Or 311 torr, which is the same thing as a millimeter of mercury. If we wanted to convert that to atmospheres, we could divide by 760. And you get that for the partial pressure of orange. If you're looking at the blue, it would be 3 over 9, and if you're looking at the little kind of pink and green, it would be 2 over 9 times the total pressure. So that's generally how you use this. I want to look at this a little bit more serious manner where we're looking at the whole PV equals nRT on the next video. Thank you so much.